Today we are learning 11.2 lesson, techniques for evaluating limits. Now in general you still need to understand the concepts of 11.1 and how limits of f of x as x goes to 3, what that means for you to complete this lesson. So first, there's a couple steps here that we will follow. Now, not every problem is going to take 4 steps. The first step is plug it in, direct substitution. If you get 0 over 0, though, when you plug it in, then you got to keep going down the list, right? So it's going to be the step of what's the easiest things to do. But once you do one of these steps, if it simplifies out, then you have to go back up and substitute again. Just a heads up. So if we get a number, the number is the answer when we plug it in, right? So like if we plugged in x is 3, instead we got 5 over 7, 5/7 would be our limit. Step 2, dividing out. This is basically factor and simplify. So factor the numerator and denominator. If something simplifies out, then we go back to step 1 and substitute it in, our x value in, and then we'll get, if we get a number, done. If it's not possible, you keep going, right? If we can't simplify, then we keep going, and then we're going to go on to rationalizing technique. If there's a square root, not limited to the denominator here. If it's a numerator or denominator, we're going to try to rationalize. Now, most of the time, it'll be something like, let's say, 1 plus the square root of x minus 1, right? In that situation, we're going to be multiplying by our conjugates to get this to work, because we can't just get 1 square root out. Generally, step 2 and 3 mean that the problem is not simplified. Even if it doesn't look simplifiable, we need to simplify it, and once we simplify, then we can plug it back in. Step 4 is use your calculator. Basically, use a graphing utility and try to assess the limit from that, or using the table. So moving on. First one, evaluate using direct substitution. The limit of 5x squared minus 3x plus 2 as x approaches negative 2. Direct substitution means plug it in. Everywhere there's an x, you plug in a minus 2. If for some reason you still have an x left in your answer, that means you did not plug in minus 2. So make sure each part that has an x gets a minus 2. That's the most common error I see. So 5 times negative 2 squared minus 3 times negative 2 plus 2. Negative 2 squared is 4, so 5 times 4 is 20. Negative 3 times negative 2 is 6. 20 plus 6 plus 2 is 28, and that is our limit because we got a nice number. Next, x cubed plus 3x minus 2 over x plus 1 as x goes to 1. We're plugging in 1, we get 1 cubed plus 3 times 1 minus 2. So 1 plus 3 minus 2, 4 minus 2 is 2, all over 1 plus 1, which is 2. And 2 over 2 equals 1, and there's our limit. Limit is 1. Pretty straightforward when it comes to direct substitution. Next, evaluate using the dividing out technique. Now, dividing out, again, as I mentioned before, is generally used as factoring. So we got to plug in first minus 2 to see if it works. You always plug in first. Okay, so if I plug in minus 2, I get negative 2 squared plus 10 times minus 2 plus 16 over negative 2 plus 2, and we get 0 over 0, which means more work. Move on to the dividing out. Now, factoring the top, we got numbers that multiplied equals 16, add equal 10, and the two numbers I found are 8 and 2. 8 times 2 is 16, 8 plus 2 is 10, and so the top is going to be x plus 8 over x plus 2, x plus 8 times x plus 2 all over x plus 2. And clearly, these will cancel. That's why we got 0 over 0. And now we have x plus 8, and I bring this back. Some teachers will say you need to write it every single step. I say after you plugged it in here, like this is, we were plugging in minus 2 here, it got zeros. You need to simplify before we plug it in again. So that's why I typically won't write limit as x goes to negative 2 for every step. Some teachers may differ in this, just a heads up. So x plus 8 is what we got. Limit as x is minus 2, plugging minus 2 in, right, back to step 1. Negative 2 plus 8 is 6. So the limit of this is 6. Next, same idea with x squared plus 4x minus 32 over x minus 4 as x goes to 4. We plug it in, 0 over 0, so that means more work, right? 16 plus 16 minus 32 is 0, 0 over 0. The top, numbers multiplied equal minus 32 add equal 4 are going to be plus 8 minus 4, so x plus 8 times x minus 4. The x minus 4s are going to cancel, and then we get limit of x as x goes to 4 of x plus 8, and then we plug 4 in, 4 plus 8, and the limit is 12. So again, we always plug in first. We need to get 0 over 0 before we can do which step. And again, what step you do depends on what you end up with. This point here, this looked factorable, so we factored and used dividing out technique. If it doesn't look factorable, like say the next one, then we're going to have to use square roots. We're going to have to rationalize, even though it tells you right here, as you get doing more and more of these, it says evaluate the limit. You just have to look at what they give you. Can we factor this? Doesn't really look factorable to me, but we can simplify by multiplying by the conjugate of our numerator. But first, let's plug it in. So plugging in x is 2. 4 minus 18 minus 2 square root. Square root of 18 minus 2 is the square root of 16, which is 4. Bottom, we put in 2 down here as well. So we get 4 minus 4 in the numerator. 2 minus 2 is 0. 0 over 0 tells you more work. And now this is where it is. You rewrite what's the top and bottom. And now we're multiplying both the top and bottom. Notice this bottom is fine. Does not have a square root. This is what is causing us to look, it's actually not simplified, but this is why, because this is preventing us from looking simplified, as odd as this is. So we're going to multiply by the conjugate, right? We can't just square it, because then we'd still have a middle term. We can't multiply by the same thing, right? That would be squaring it, because of what I just said. So we're conjugate, right? A minus b times a plus b gives you a squared minus b squared. And if we have this as minus b squared, the square roots are going to cancel. So multiplying top and bottom by 4 plus the square root of 18 minus x. And we get x minus 2 times the mess, 4 plus square root of 18 minus x on the denominator. Now the numerator, 4 times 4, 16, minus. This quantity squared is just going to be minus the square root, sorry, minus the quantity 18 minus x, right? Because square root squared, 1 comes out. So 16 minus 18 minus a negative x is plus x. 16 minus 18 is minus 2, and this top is actually equal to x minus 2 over x minus 2. There's where we were getting our 0 over 0, right? As much as it didn't look like that, that is literally what it's simplified to. And oddly enough, yep, we're going to have a square root in the denominator, but that's okay. We're not rationalizing again. Once we've canceled something out, we plug back in. So now I'm going to rewrite equals the limit of x going to 2 of what we have, 1 over 4 plus the square root of 18 minus x. Now I will always tell you, as odd as it is, to leave it like this. Most of the time when we plug our 2 in, it will clear things up. This will be a perfect square and we'll get an answer. If it doesn't, you can rationalize at that point. Okay, so don't rationalize until your final answer ends up with something like 3 over square root of 5. Then we would rationalize. In this case, 1 over 4 plus the square root of 18 minus 2, plugging in 2. 18 minus 2 is 16, like we did up here. And square root of 16 is 4, so 4 plus 4 gives us 8. And our answer is 1/8. Okay, so you wouldn't think from the start it's going to be that, but it ends up being a pretty nice number. Next one looks a little messier. Limit as x goes to 0 of the square root of 7 minus x, quantity minus the square root of 7 all over x. Now clearly plugging in 0 is going to give us an issue in the denominator. The numerator will also follow. Square root of 7 minus square root of 7 is also 0, so more work. And again, this is something I believe actually came from college. Whenever you get 0 over 0, it always means more work to do. So in this case, multiplying by the conjugate in the numerator, we get square root of 7 minus x minus square root of 7 over x times square root of 7 minus x. Again, conjugate just means the term between, sorry, the sign between the term flips. So square root of 7 minus x plus square root of 7 over itself, multiplying by 1, and we get 7 minus x minus 7, right? We only had one piece, so I didn't add the parentheses there, but we get 7 minus 7 is 0, so I get negative x over x times square root of 7 minus x plus square root of 7. And the x's cancel, but the top is negative 1. And so now we have limit as x goes to 0, bringing that back, of negative 1 over 7, square root of 7 minus x plus square root of 7, right? This is why I have to make sure this goes on top and bottom. It's typically what's left over. And then plugging in, negative 1, square root of 7 minus 0 plus 7, I get negative 1 over 2 root 7. This is when we rationalize. Square root of 7 not nice. Multiplying by square root of 7 top and bottom, we get negative square root of 7 over 2 times 7, which is negative root 7 over 14. A couple more problems left. And we have the limit as x goes to 4 of x minus 4 over square root of x minus 2. Now this time we have some denominator work to do, and it looks like our goal is to get x equals 4. And so plugging it in, 4 minus 4 is 0, square root of 4, 2 minus 2, also 0. So more work. X minus 4 over x square root of x minus 2, so multiply by square root of x plus 2 on top and bottom. And again, notice I never multiply these together. It's always an understanding that something's going to cancel. Oh, and what do you know? Square root of x times square root of x, x. Negative 2 times plus 2 minus 4, because it's a minus b times a plus b. Yep, there's an outer and inner term that cancels. And now plugging back in, I got square root of x plus 2 because these canceled. And square root of 4 plus 2 gives us 2 plus 2, and the limit is 4. So we indeed matched. And now we'll visit the last method for solving, which is use your calculator. The limit of x goes to 0 of x plus 1 to the 1 over x. Now using technology to evaluate, we've got the limit as x goes to 0 of x plus 1 to 1 over x. Now using your calculator with this one, we would typically, pulling up again my graphing calculator here, we're going to click the graphing part. We've got already plugged in. Right, I put in x plus 1 to the 1 divided by x, and that's my graph, right? So now if I graph it, it actually looks like a decent number. It looks like we should get an answer here. However, again, just a quick note, if we trace the value, right, looks like I already have, we got, if we plug in x is 0, y doesn't exist, right? We can't have 1 divided by 0, undefined, being our exponent. But from here, we can trace values from the sides, right? So normally we do values less than 0 and values above 0. So by plugging those in quick, it would look like negative 0.1, enter, and now it tells me. By the way, this shows up because I did second trace value. So second, the trace button, which would be calc now, because that's what we're in blue, and hit on our value lets me plug in the calculator we're calculating instead of me having to plug it in. So negative 0.1, a little to the left, 2.867, a little further, negative 0.01, getting closer and closer to that 0, 2.7319, and now negative 0.001, that's third decimal, so positive 2.719 about is where we're at. And then doing the other side, so now 0.1, positive, 2.59, 0.01, 2.704. So we're getting close to that 2.71. I need another 0 here, pardon me. And then we get 2.7169. So it's about 2.717, maybe 8 if we kept getting closer and closer. So both sides appear to be approaching this 2.718 something, right? And this is actually E, right? 2.71 ... is E. Both of my sides appear to be approaching 2.718, so the limit is that value. We have one last topic to cover in today's lesson, and it's limits from one side. Now, one-sided limits specifically, the limits we talked about in previous lessons were the limit from both sides. Does it exist? Now, there's symbolically a way to say, is there a limit from the left side? Is there a limit from the right side, right? Because we've already done this definition. The limit exists if and only if the limit from the left side, which is c to the negative sign, that's it, equals the same value as, right, equals L, the same value as the limit from C plus, which is from the right side, right, above the X value. So if the left and right match, then they exist. So here's how that works, right? Let's say we have the given graph, right, is our function, and we are evaluating at X is 3. Well, on the left side of the graph, my y value appears to be 3. So limit of f of x as x goes to 3, not negative 3. 3 negative means the left side of 3 appears to approach y is 3. Then I need to check what about the right side of my graph. So the right side would look like limit of f of x as x goes to 3 positive. Right, so we're talking about this part from the right side of 3, and looking at our y value, it looks to approach, I have it already marked here as 10, so this approaches 10. These numbers do not match, so if we were looking to see if the limit existed, we would say, these don't equal, therefore the limit at 3 does not exist, DNE. And so we'll do one more of these problems, and then we move on to this last one. Find the limit if it exists of limit as x goes to negative 3 of the absolute value of x plus 3 over x plus 3. So clearly we can't use the methods we learned earlier this lesson to find the limit. So we rely on table, right? Because if I plugged in negative 3 plus 3 is 0, and 0. More work, right? And so I look at the limit as it's from the left side. Sorry, this one's the right side, above. I got an error there. That should be a negative sign. No, pardon me. I am correct. It is above, right? Negative 2.9 is bigger than negative 3. So, okay, I did the symbols right, just opposite order. So above negative 3 would be negative 2.9, negative 2.99, and so on. But if you plug it in, negative 2.9 plus 3 is going to be 0.1. Negative 2.9 plus 3, also 0.1. 0.1 over 0.1 is 1. Now, what's going to change is on the right side, we're going to approach negative 1 instead of 1. Why? The denominator is going to be negative. The numerator is going to be positive at all costs because of the absolute value. And so we get negative 1 on the right, positive 1 on the left. Limit does not exist. And one more piecewise function to finish it off. A non-graph piecewise function, limit of f of x, if f of x is x plus 1 for x less than 3 and 2x minus 4 for x greater than or equal to 3. So on the left side, less than 3, we got 2.9, 2.99, and when I plug them in, 2.9 plus 1, 3.9, 2.99 plus 1, 3.99, right? Just getting closer and closer to 4. So we'll say the limit of x goes to 3 from the left is 4. Now on the right side would be greater than 3, right? If we plugged in, say, 3.1 or 3 or 3.01, right, seeing where it approaches, I get 2.02, 2.22, so the right side approaches 2. 4 and 2 do not equal, so again, the limit does not exist as we approach these values. That wraps up this portion of 11.2's lesson.